Hello everyone, I am Sagar Chipa, a final year student of MSc Physics at Regional Institute of Education, Mysore. So in this video, we are going to talk about the statics of a Smectic A materials. So we'll be looking at the liquid crystals and we'll have the basic understanding of what are the Smectic materials, what are the Smectic A materials, and at the last, we'll extensively talk about what are the statics of a Smectic A materials. So let us see one by one. So first of all, let us see what are the liquid crystals. Liquid crystals are a state of matter that exhibits properties between those of conventional liquids and those of solid crystals. They have an ordered molecular arrangement like a crystal, but they can flow like a liquid. There are several types of liquid crystals, phases, including nematic, smectic, and cholestatic phases. Liquid crystals are widely used in various applications such as display technologies like LCDs, sensors, and optical devices due to their unique optical and electrical properties. Now let us see what are the smectic liquid crystals. Smectic materials are a type of liquid crystal materials that exhibit a specific type of a molecular ordering. They are named after the Greek word smektos, meaning soap, because of their layered structure, reminiscent of soap molecules arranged in layers. Smectic materials have molecules that are organized into layers, and within each layer, the molecules have a specific orientation. There are several different phases of smectic materials, including smectic A, smectic B, smectic C, and other, each with its own distinct molecular arrangement and properties. Smectic materials find applications in various technologies, including liquid crystal displays, sensors, and optical devices. So now let us see what are the smectic A materials. Smectic A materials In the smectic A materials, the arrangement of atoms within molecules determines the overall structure of the material. Smectic A materials are composed of molecules that are organized into layers, with each layers containing molecules aligned in a specific direction. The atoms within these molecules can be arranged in various configurations depending on the molecular structure and interaction between atoms. The specific arrangement of atoms within smectic A materials can vary widely depending on the chemical composition of the molecules involved. For example, smectic A materials may consist of rod-like molecules, disc-like molecules, and other shapes, each leading to different packing arrangements within the layers. Additionally, the interaction between molecules such as van der Waals forces, hydrogen bonding, and electronic uh, interactions also influence the arrangement of atoms within smectic A materials. Overall, the arrangement of atoms in a smectic A materials contribute to their unique properties, including their ability to exhibit both fluid-like behavior and long-range order, making them valuable for various applications in electronics, optics, and material science. So now we'll see what are the statics of a smectic A. So first of all, let us understand what do we mean when we say the statics of a smectic materials. The statics of a smectic A materials refers to the study of their equilibrium properties and behavior when they are not undergoing any dynamic changes. This includes characteristics such as the arrangement of a molecule within layers, layer thickness, orientational orders, and interaction between molecules. Understanding the static properties of a smectic A materials is crucial for predicting their behavior in a different condition and for designing devices that utilize their unique properties, such as LCDs and sensors. Static properties are often analyzed using techniques such as X-ray diffraction, microscopy, and spectroscopy. So first of all, now let us see all the properties, the statics of a smectic A one by one. So let us see what are the arrangements of a molecules. The geometry of smectic A materials is characterized by the arrangement of molecules into layers. In the smectic A phases, the molecules are organized into layers that are parallel to each other. Within each layer, the molecules are oriented in a specific direction, but they can flow past each other within the layer. The layers themselves can slide past one another, giving the material some fluidity while maintaining a degree of order. This layered structure is often visualized as sheets of molecules stacked on top of each other, akin to deck of cards. Let us see some points. So first is layered organization. We have already know that the arrangement of a molecules in smectic materials are layered structure. Imagine a elongated rod-shaped molecules lined up parallel to each other. These molecules form distinct flat layers stacked upon one another. The forces between the molecules within a layer are stronger than the forces between the layers. This anisotropic interaction creates the separation between the layers. The second point is long-range positional order within layers. Within each layer, the center of mass of the molecule exhibit a high degree of positional order in two dimensions. This means the average position of the molecule in the plane of layer are well defined, creating a crystal-like arrangement in the plane. The long axes of the molecule within the layer tend to be aligned roughly parallel to each other, but this order is not perfect and only extend over a short range. Fluid motion within layers. Despite the order, the molecules are not fixed in their positions. They can still move somewhat within the plane of layer, exhibiting fluidity. This allows them to rearrange and flow to a limited extent. Isotropic versus anisotropic properties. Due to the layered structure, symmetric A materials exhibit anisotropic properties. This means their physical properties depend on the direction of the measurement. Now let us see what are the layer thickness in the statics property of a smectic A materials. The layer thickness of a smectic A materials is a crucial property that influences their behavior in a various applications. So let us see it points by point. So the first point is typical range. Smectic A phases are characterized by layers of elongated molecules with a relatively ordered arrangement. The thickness of these layers typically falls within the range of 2 to 5 nanometer. Now let us see the variation. This value can vary depending on the specific smectic A material and its molecular structure. Factors like the length and shape of the molecules as well as the intermolecular interactions can influence the layer thickness. Temperature dependence. The layer thickness of smectic A material is also temperature dependent. In general, as the temperature increases, the layer thickness tends to increase slightly due to thermal expansion. Now let's see the measurement techniques of layer thickness. There are various techniques for measuring the layer thickness of a smectic A phases. Some common method includes X-ray diffraction, neutron scattering, and atomic force microscopy. The layer thickness is a critical parameter for understanding the optical properties of a smectic A materials. It plays a role in light diffraction and influences the applications in the LCDs and the other photonic devices. Now let us talk about the orientational order of the molecules. In smectic A materials, the orientational order of the molecule is a key characteristics, but it differs from the positional order within the layers. Here's a detailed explanation. The first point is short-range order. Unlike a perfect crystal, smectic A phases exhibit only short-range orientational order. This means the long axes of the elongated molecules within a layer tend to be aligned roughly parallel to each other, but this alignment is not perfect and extends only over a short distance. The molecules can deviate slightly from this preferred orientation, leading to a more fluid-like arrangement compared to a solid crystal. Now let us see the factors affecting this order. The degree of orientational order depends on several factors, and one of those factors is molecular shape. The rod-shaped molecules with a strong intermolecular interaction tend to exhibit better orientational order. The second reason is intermolecular forces. Stronger interactions like dipole-dipole or hydrogen bonding can promote better alignment. And the last point is temperature. As temperature increases, the thermal fluctuation can disrupt the order, leading to a decrease in the average alignment. So let us see the impact on properties. The short-range orientation orders in a symmetric materials still plays a significant role in their properties. So we can understand it by using the anisotropic behavior and the optical effects. It contributes to the anisotropic nature of a symmetric A materials, where properties like electrical conductivity and refractive index depend on the direction. The optical effects. The partial alignment can influence how light interacts with the materials, impacting application and liquid crystal displays. So while not perfect, the short-range orientation order in a symmetric A phases is a crucial aspect that distinguishes them from isotropic liquids and contributes to their unique properties. Now let us understand the last static properties of a symmetric A materials. The interaction between molecules in a symmetric A materials are a complex interplay of various forces that ultimately lead to the characteristic layered structure and properties. So let us understand it one by one. The dominant forces are dispersion forces or London forces. These weak temporary attractive forces arise due to fluctuation in electron distribution within the molecules. They play a crucial role in holding the elongated molecules together. within the layers of an Smectic A phase. Now let us talk about the secondary forces, the secondary interaction. It can be considered as a dipole-dipole interaction and a hydrogen bonding. If the Smectic A molecules possess permanent electric dipoles, these dipoles can interact favorably when aligned head to tail or tail to head, promoting a preferred orientation within the layer. Now let us see the hydrogen bonding. In some Smectic materials, hydrogen bonding between specific functional groups on the molecules can create strong directional interaction, further stabilizing the layered structure and influencing the orientation. Now let us see the steric interaction. Repulsive steric interactions come into play when the electron clouds of neighboring molecules get too close. These interactions help maintain a certain average distance between the molecules within the layer and prevent them from packing too tightly. The balancing act. The interplay between these attractive and repulsive forces determines the overall organization of the molecules. The dispersion forces and the other attractive interactions favor the formation of layers, while steric repulsion prevent overpacking and ensures some fluidity within the layers. The temperature dependence. As temperature increases, thermal fluctuation can disrupt the interaction between molecules. This can lead to a decrease in the orientation order within the layers and eventually a transition to the isotropic liquid phase. Influence of molecular shape. The shape of the molecules in a symmetric A material phase significantly impacts the interactions. Rod-shaped molecules with a large aspect ratio tend to form well-defined layers due to stronger anisotropic interaction along their long axis. So understanding this interaction is crucial for designing and manipulating symmetric A materials with the desired properties for various applications. So these were all interactions for symmetric properties of a uh, statics property of a symmetric A materials. That's all. Thank you so much.